What's up everyone, today we're going to talk about comparison functions, and these are the type of functions that we will be using in control theory and many of the theorems that we will be discussing in this playlist. That will be the first video in this playlist. So this is, there are four class of functions, class K, K infinity, L and KL. So let's begin with the definitions. Class K function, so we have this alpha function, and then let me get the another color. Okay, so we have this function which goes from not R positive directly, it doesn't need to be, and we will look at another function that goes from R positive to R positive, but this one, due to the reasons that will be obvious in a moment, goes from a finite, but this part is open, finite section of the R positive to basically R positive. Okay, so another thing that it needs to be continuous, all right, and then where a must be a positive number, of course, and then it can be infinity, so it can be like basically R positive. This is what we just mentioned, and then this function is said to be of class K if there are basically three items that we need to satisfy, and it should be 0 at 0. Okay, that's quite understandable or quite easy to grasp, and then it should be positive. Okay, then alpha is secretly increasing with respect to R, like with respect to its only argument, of course. So now that I think about it, like that is kind of redundant, but since it is 0 and then it is strictly increasing, yeah, of course that needs to be the case. So something like that. Of course that doesn't mean, like I don't even need to state that, but that doesn't mean that alpha R would be infinity, right? That doesn't mean that. I mean, you can strictly increase, but you wouldn't go to, like you wouldn't reach to infinity as t goes to infinity. So, right, there are many examples for that. Okay, so class K function, let's look at these examples. For example, this is the type of example that would go to infinity. Okay, and that one is also the case. That one, however, if you take the derivative, if I'm not mistaken, it must be something like this. And like, I mean, the argument is not x, but you get the point. So for or x, it is obvious that this is a positive. So that means this is a strictly increasing function. However, by the way, this is the type of function that we are all familiar with. Let me get another color. This goes to pi over 2. Okay, as r goes to infinity. So, really nice example of a function strictly increasing, but do not go to infinity as the argument goes to infinity. And then that might be like a easier function to understand. So class K infinity, okay, as you can imagine, this has something to do with class K. So this is a subset, like the function set. This K infinity is the functions where a set of functions where each of them is class K infinity, and this is a subset of class K functions. All right, so again we have that, but this time we literally have from R positive to R positive, and then there are two items, this needs to be of class K. And then the second thing, it goes to infinity as R goes to, the argument goes to infinity. Okay. So, by the way, I will upload this PDF on GitHub. So check the link down below to access that. And then, okay, it will be 0 at 0. It will be strictly increasing. However, it will go to infinity. That's it. Alright, so let's look at some of the examples. Again, that makes sense. R, of course. I mean, that is also a special case of these type of functions. That also makes sense, right? This is like only positive, for example, square root of R. Like, it is obvious that that is what we would have. So it would go to infinity. And this function is, you can also check, like this is increasing, and then it would go to infinity. All right. So class L functions. So this is a function beta. It needs to be continuous, of course. It needs to be continuous from R positive to R positive is of class L if it is strictly decreasing. It needs to be decreasing plus as t goes to infinity, this goes to 0. So like we are expecting some type of, like it needs to start somewhere, but as t goes to infinity, it needs to go to like 0, right? That is it. So we are expecting not necessarily like exponential type of decay, but some type of decay that would reach to 0 as t goes to infinity. Okay, so these are the type of examples, and you can check and then see, like by taking derivative and then showing that for the positive values of t, the derivative of the function is like negative, hence like secretly decreasing. And also you can also show that as t goes to infinity, this will go to 0. All right. So now the class KL function. We will be using class K and class K infinity. I'm not sure about like the direct usage of L, but I feel like L is the type of function class that will be used in the definition of class KF only. But I'm definitely sure there might be like another use case of that in control theorem. Okay, so anyone or everyone can find a use in some type of purpose in control theory, I think. All right, so after this quote-unquote motivational expression statement, let's go and look at the class K add function. So not directly from R plus cross R plus, okay, we will be mapping to R plus, and then this continuous function is called class KL if for each fixed, let me just write it down, for each fixed t, this needs to be class K. Okay, and for each fixed R, the first argument, if we fix that, this becomes class F function. All right, so this is, I would say, like implicit definition, or rather, there should be a definition, I feel like, that wouldn't require us to know about class K and F, right? Let's look at that definition. Yes, I should set definition 1 and then definition 2 or something. So yeah, it is that type of definition. First of all, for all t, this needs to be like that equality needs to be satisfied, right? And then this basically these two comes from the class K part, and then this two, the final two, comes from class L part. Okay, and it will not make any sense when you look at it. Like looking at the definition will not give you any idea, and that this is the case for any, I think, like, subfield of math. And so let's check without even like delving into the details or rationale behind it. Let's look at some of the examples. So these are the type of examples, and if you can notice, they are in like some type of function. Let's say in this case r, and then some type of function t. Like they have that type of form. So and then that's form, this form, okay, this is the class K part, and then this is the class L part. Okay, so if you notice, this is something decreasing over time, and then this is something increasing over time. Like for fix, when you fix the other arguments of this function, this is what you would have. And again, the same thing for this. And we basically have one class K function and one L function. We just multiply that to have this class K functions. All right, so let's look at some of the use cases. I shouldn't even have said like examples. These are like the use cases of those comparison functions. Again, there are millions of maybe I might be exaggerating when I said that definition of the open function, and this is one definition, right, where we will be using comparison functions. So consider a system of the form that type of function, and here this is switching or switched type of function. And when we say switching, and recently I was reading a paper and then I noticed there was a distinction between that. And when we say switching system, the dynamics are being switched, like changed, by a signal, by an exogenous signal that we have no control over. However, switch signal, or rather switch dynamical system, is we have some like dynamics and then we are switching between them, but the way we switch is governed by like internal signals, right? Okay, let's say imagine R2, right, x1 and x2. So if we are here, the system should be governed by f1 of x, and if we are anywhere else, the system should be governed by this part. And then if we are here or if we are there, and for that we could have that type of function, right? So this is the switched or switching type of dynamical systems in a nutshell. Of course, like, I don't even need to mention they're crazy complicated compared to the linear ones, etc. Right, so this basically means that, so we can have that type of fn many non-linear. None of them has to be linear. So if you think about it, that's like a, I don't know, crazy complicated type of dynamical system, because not only we have non-linear dynamical systems, we have multiple of them, and the system is switching between them, right? So let's continue. Okay. Those functions though, they need to satisfy this equilibrium point condition. Okay. And then, because they need to agree, right? So this is the plant, and then continuous function is psi from Rn to R is said to be a Lyapunov function if, okay, so these are our conditions. First of all, this is the boundedness condition, where K1 and K2 comes from class K, they're of class K functions, okay, and then here this part is these properties are there to basically explain, well, the properties of alpha. I don't want to make a definite, like I got this definition from this really nice paper and influential paper from Blancini and then Savarnan, and then I don't want to make a definite claim about it, but I am almost sure, I have suspicion rather I should say, that alpha is a class KL function. Okay, but let's go with that. So this is the inequality that our Lyapunov function psi needs to satisfy, and then let's look at that alpha function, right? And we have two arguments, and first of all, it needs to be a continuous function, right? Then for fixed t, when you fix that, it needs to be circularly increasing with respect to the first argument, okay? And then when you fix the first arguments, it needs to be strictly decreasing with respect to the second argument. Okay, so I'm guessing that you are kind of getting some type of feel, and or these type of properties are reminding you of something. And another thing, for all like for all first argument, when the second argument is 0, the output of this function is it must be equal to the first argument. Okay, got it. So this is, I am assuming it is either like KL or some special type of KF. Yeah, okay. Anyway, so I don't want to dwell on this because we will be using that, right? Okay, and then we will be using that definition in this playlist, maybe probably in the third video or something. And because there's something we're going to be proving, what we will be proving is the following. And so we have a system, and then autonomous system, and to prove some type of stability, we would need to have some type of Lyapunov function. And I'm gonna be honest with you, I didn't know about this, like definitely, but Lyapunov function always doesn't need to be a convex function. So for some subset of dynamical systems, Lyapunov function bound to be convex one. However, for some of them, no, that is not the case. And in fact, there are some systems, there are some criteria, and then we will be looking, these are the type of things that we will be talking about in this playlist. There doesn't exist any convex Lyapunov function. There exists some type of functions that are not convex, and the system is stable, and then those type of non-convex Lyapunov functions can be used to prove the stability. Okay, so JS, what's JS is not the thing that is expensive right now. This is global asymptotically stable. So this is the definition, or another type of definition for JS. The origin is globally asymptotically stable for given autonomous dynamical system if there exists a function beta of KF function class such that for all initial condition the system needs to have that property. And if you notice, this is like implicit definition, right? Like, first of all, you need to compute kf, or you need to have a function beta, and more importantly, you need to basically solve the system, right? Because you have a dynamic system, and then basically you need to solve that, which is why we have the Liopanov function to begin with, because we don't want to solve, because for some functions, for some dynamic systems, it is impossible to solve, right? And so this is a type of definition, type of criteria that wouldn't help you that much, but this is our starting point. From this starting point, we will be deriving some type of criteria that would be helpful for us to determine the stability of a given system, or global asymptotic stability property for a given system. Okay, and then this, if you notice, now my notes are like much more organized. So I even put the source in each page and stuff. All right. So this is our third definition, a Liopanov function. Okay. For a given system, is continuously differentiable function, right? Such that there exists alpha 1 and alpha 2 from k infinity function class, and then continuous positive definite function rho, and such that those two properties are held and then are satisfied. First of all, if you notice, we need to have v, we need to have alpha 1, we need to have alpha 2, and then we need to have rho function. So not only we need to have like v, plus we need to have like other these three functions to prove the stability, right? And here, that one is kind of understandable. Like this is, or not, I shouldn't say understandable, but this is a type of property that we have seen like many times, right? And then again, this property is also the type of property that we have seen like many times. And let's look at it one more time, and then let's go. So this is the boundedness. Like this basically tells us it needs to be positive, plus it needs to well behave, right? And since this is like k infinity, this also has some radial boundedness property into it. So let's look at that. The second definition here, a Liopanov function from Rn to R for this dynamic system is a continuous differentiable function such that there exists alpha 1, alpha 2 from k infinity, and then beta from kf. And okay, this is what we have, and then yeah, this one is kind of new, right? So here, and then this is the Liopanov function evaluated at the initial points. Okay, and I'm looking at this. I should have set like for all x O in Rn or something. Yeah, probably I should have said that. Or yeah, that expression is missing. That is correct. Yeah, I'm sure it needs to. We need to have that. Okay, so I mean, I will not, first of all, like this is the definition, right? There should be some type of like proposition that this one, like that function, the Liopanov function, that satisfy this conditions are to be used to prove stability. That is something to be proven, but okay, of course we will not get into that because we have a life. And let's go and ISS, International Space Station. No, this is input to state stability, right? So this is the type of stability condition where you have some type of input, right? Usually you have like a box. You have like a closed system. X dot equals f of x. This is the dynamic system that you have, and then this is like a box. But when you have x dot equals f of x, so you have state plus you have some input entering into the system. Okay, for this you look at, I don't know, asymptotic stability, but for this you need to look at ISS. Okay, let's check the definition. Consider a time invariant system, okay, of ODE. By the way, yeah, this is the source is Wikipedia input state stability. All right, so since this is Wikipedia, this will be like as general as possible. So there will be, and I'm just giving you like a trigger warning. Yeah, there will be some terms that you are not familiar with, and maybe you shouldn't be familiar with if you would like to have a life. All right, so okay, this is basically we have a dynamic system, and f is before f, this u is the best measurable, essentially bounded external input. So in a nutshell, first of all, like at the moment, hopefully one day I will be able to like explain why this is important, what those things are, like in a meaningful way. But at the moment I am gonna go over it, and I'm not gonna pretend that I know like a lot about it, but that is the type of thing that would let you take the integral or something, right? Because anytime you're taking integral, there needs to be some type of like the function or the signal that you're integrating needs to satisfy some type of measurability properties, and that's it. So basically you can kind of translate it into the saying well behaved or something, okay? And essentially bounded is, first of all, essentially, why not bounded, why not essentially? And so immediately the moment that you see essentially, that tells you that we are dealing with like strange, or we are trying to either act like we are really smart, or there are really reasons for that, why, or we are having this definition that is really general, and then one might even say that do we even need that question mark? And yeah, but we will not get into that type of discussion. So essentially bounded is bounded, like f of x is bounded for all x in sets almost everywhere, AE. What does that mean? The measure of the sets that doesn't satisfy this criteria is 0. And I'm not gonna say anything, other than this statement. So let's pretend that it is a nice and function, right? External input, all right? So f is a Lipschitz okay, we kind of know what the Lipschitz is, right? Lipschitz continuous with respect to first argument, uniformly with respect to the second one. Okay, that kind of makes sense, all right? So I mean, we know what Lipschitz continuity is, and in fact, like speaking of that, hopefully, I'm not sure when will I do that, but one of my goals is to do that like before I die, and have a playlist where I talk about like math for control theory, and do not hold your breath like for that. But I'm serious. I would like to do that before I die. Yeah, if I really die and then before doing that, I would be, I don't know, yeah, upset from the other side. So this ensures like these type of properties that U and F needs to satisfy, and they ensure that there exists a unique, absolutely continuous solution of the system. So, existence and uniqueness stuff that has to do with that. And then I know this is like a informal way of making that statement, but let's go with that. System is called input to stable ISS, Okay, now here's math is coming. All right, there exists gamma, which is class K, beta from KF, and such that for all initial condition and for all given admissible control signal for all t, this is something that we need to satisfy. And as you can imagine, first of all, let's try to understand what this is. And we basically, like if you ignore that part, we basically seen that part. And this was like when you have 0 inputs. This is what we need to have like JS, global asymptotic stable property, right? And when we have, however, inputs, our bounds, of course, need to, like, yeah, we need to have a higher bound, and in a way you can kind of rationalize it in your heads, right? Okay, you can basically, I'm teaching you, like, this is why this YouTube playlist or my videos are very important. I'm not only teaching you, I'm also teaching you how to trick yourself into believing that you actually understand the type of like equalities, type of like properties, theorems that you actually didn't. So yeah, thank you, or you're welcome. Function gamma in the above inequality is called gain. Okay. Function gamma in the above inequality is called gain, and that kind of makes sense because we have the input signal and then we are amplifying that, right? Okay, so we can go again. This is the source, and I think, yeah, that's it. All right, and don't forget to subscribe and have a nice one, I guess.